Section: Introduction. In this section, we discuss the versatility of graphs as mathematical structures that can model complex interactions in various fields, such as life sciences and social sciences. This versatility highlights the need for specialized machine learning methods to derive valuable insights from graph data. Recently, message-passing graph neural networks, or MPNNs, have become the leading approach for machine learning on graphs, gaining attention at major conferences due to their promising results in applications like antibiotic discovery and weather forecasting. However, we believe that for graph learning to remain significant, current benchmarks must align with transformative real-world applications. Many existing datasets focus on narrow areas or tackle problems that lack practical relevance. For example, popular benchmarks often use two-dimensional molecular graphs, overlooking important three-dimensional structures. Additionally, studies frequently report high performance on synthetic datasets like zinc, which do not provide strong justification for their graph-based methods, complicating their usefulness. We also note that empirical studies in graph learning often face methodological issues. Inconsistent dataset splits and evaluation methods hinder valid comparisons, and small datasets can lead to high variance results with limited statistical significance. These challenges, along with a lack of large and diverse datasets, have restricted the scalability of MPNNs and GNNs to larger pre-trained models. In this position paper, we argue that graph learning needs to significantly revise its datasets and benchmarking practices to maintain its relevance. We will outline the current shortcomings in graph learning benchmarks, such as the lack of transformative real-world problems, an overemphasis on specific data types, and fragmented evaluation protocols. We will also propose actionable recommendations for the graph learning community. Based on our evaluation of current benchmarks, we will establish new baselines and reference models for molecular prediction tasks and large-scale datasets, while exploring in-domain and cross-domain transfer in a pre-training and fine-tuning context. We will provide a critical overview of the current state of the field and highlight 4 key shortcomings in graph datasets and benchmarking practices, along with potential solutions. Graph learning encompasses various approaches, primarily focusing on graph-level and node-level predictions. In graph-level predictions, we train a GNN on a set of graphs to make predictions on new graphs. In node-level predictions, we aim to predict outcomes for nodes within a specific graph, using either a transductive or inductive setup. In the transductive case, we have a single graph with some nodes labeled for training, while in the inductive case, we train on a set of graphs with labeled nodes to predict labels for nodes in unseen graphs. We can also define edge-level or link prediction and graph generation, which involves creating graphs that reflect a specific data distribution based on a training dataset. We acknowledge earlier efforts to improve benchmarking for GNNs, such as the introduction of a suite of real and synthetic graphs covering various tasks and an attempt to standardize evaluation protocols. However, many tasks still rely on graphs derived from existing datasets or focus on small synthetic graphs with limited performance variation. The suggested model size limit of 500,000 parameters aimed to test inductive biases, but this restriction is less relevant in today's deep learning landscape, where larger models often perform better. The Open Graph Benchmark, OGB, was introduced as a comprehensive suite of datasets across different domains and tasks, promoting standardized benchmarking practices. However, many datasets still fall short of addressing transformative real-world applications, often lacking critical information or inducing biases that do not benefit generalization. While OGB has some impactful benchmarks, the research community has not prioritized them, likely due to the challenges of scaling complex architectures or the focus on specific settings like heterophilic networks. We also note that some proposed benchmarks aim to evaluate the long-range capabilities of GNNs, but issues with hyperparameter choices have led to overestimated performance gaps. Additionally, while some efforts have been made to improve evaluation protocols, they often focus on small datasets. In 2D graph generation, many studies still rely on datasets like QM9 or ZINC250K, which are considered solved, and the widely used Spectre benchmark has also reached saturation, with inconsistent reporting across studies. We will discuss these related works in more detail later. Section Summary. In this section, we highlight the versatility of graphs in modeling complex interactions across various fields and emphasize the need for improved benchmarking practices in graph learning to ensure relevance and impact. We argue that current datasets often lack real-world applicability and suffer from methodological inconsistencies, which limits the scalability and effectiveness of message-passing graph neural networks, MPNNs, and graph neural networks, GNNs. Section: Missing transformative real-world applications and supporting benchmarks. In this section, we discuss the lack of transformative real-world applications and supporting benchmarks in the graph learning community. We believe that benchmarks showcasing the true advantages of machine learning on graphs are still missing. Unlike fields like computer vision or natural language processing, graph learning lacks clear application areas since graphs often represent data with less obvious relationships. Historically, graph learning has focused on testing new graph neural network (GNN) architectures on specific datasets, particularly in the molecular domain, such as predicting properties of small 2D molecular graphs. However, these small graphs only represent niche areas in chemistry and drug discovery, where a 3D structure is more relevant for understanding properties at a quantum level. Moreover, converting raw chemical data into 2D molecular graphs can be tedious and may lead to the loss of crucial information, failing to capture the relationship between atomic arrangements and their properties. In supervised graph learning and graph generation, similar challenges arise. Most studies benchmark their methods using 2D molecular graphs, but 3D point clouds may be more suitable for real-world tasks like molecular docking. For instance, Digress, a highly cited work in graph generation, has not led to many practical applications, with most citations serving as background rather than extensions of its ideas. The field struggles with evaluating the quality of generated graphs without ground truth data, leading to a lack of application-driven focus and limited attention on important topics like generating graphs with strong structural constraints. To address these issues, we suggest that the community shift its focus from smaller, less relevant 2D molecular benchmarks to problems that are naturally represented as graphs. One promising area is combinatorial optimization, where graphs can represent problem instances, such as vehicle routing or integer linear programming. Combinatorial optimization benchmarks have clear real-world applications, allow for easy generation of large datasets, and serve as excellent testbeds for studying size generalization. Other potential areas for GNNs include satisfiability solving, recommender systems, social networks, and power flow networks. Projects like Relevance and 4DB Infer show how GNNs can automate machine learning on relational databases, while TPU graphs highlights their potential in computer systems. GNNs are also effective in automated chip design, as seen in AlphaChip, which uses reinforcement learning with netlist embeddings. However, industrial datasets, like social networks, often contain sensitive data, limiting access. Improved anonymization methods, such as generating anonymous graphs that resemble real-world data, could help. While GNNs have been used for de-anonymization, generating anonymized graphs remains a challenge. Graph generation also shows promise for design tasks, particularly through diffusion models that create heat maps for sampling solutions to combinatorial problems. Although competitive, further work is needed to enhance efficiency and understand GNN capabilities in this area. We hypothesize that for any prediction task, the counterpart of conditional generation is also valuable, provided the evaluation of the prediction is straightforward or robust enough to assess generated samples reliably. By prioritizing combinatorial optimization and graph representable problems, we can advance both theoretical insights and practical applications, paving the way for real-world impact. We also note that graphs are not always constructed meaningfully. Their effectiveness in addressing specific tasks depends on how they are built and whether the relational information they contain is relevant to the problem. Unfortunately, many commonly used graph learning benchmarks do not consider the meaningfulness or completeness of the constructed graphs. For example, The Pascal-Voc SP and Coco SP datasets use graphs that connect superpixels in a way that lacks theoretical justification, making it unclear if this approach aids object detection. In spatiotemporal datasets, like traffic networks or air quality measurements, the method of constructing graphs can be arbitrary, potentially misrepresenting system dynamics. The choice of threshold values in these cases is often heuristic, which may overlook significant connections. This highlights the need for more principled, data-driven approaches to building spatiotemporal graphs. Another example is the zinc benchmark, which contains small molecular graphs that capture chemical relationships but miss important structural details like 3D coordinates. Additionally, while relational information can be relevant, it may not always be informative for the prediction task. Recent studies have shown that some models overfit to irrelevant correlations in the structure, while others that focus solely on node features perform better. For instance, in citation networks, the connections between articles may not be as predictive as the textual similarity of their content. Section Summary. In this section, we highlight the lack of transformative real-world applications and meaningful benchmarks in the graph learning community, emphasizing the need to shift focus from niche 2D molecular graphs to more relevant problems like combinatorial optimization. We argue for the importance of constructing graphs that accurately represent relational information to enhance their effectiveness in practical applications, while also addressing challenges in graph generation and the need for better methodologies in graph construction. Section: Suggested Remedies. In this section, we suggest that almost any real-world phenomenon can be represented as a graph, but not every relational structure is equally useful or predictive. We should design benchmarks that systematically consider this idea, keeping in mind that not everything that can be modeled as a graph should be. When we propose new benchmarks, we need to explain the benefits of using a relational modeling framework and how it compares to other methods. We should also clarify the features of nodes and edges and the reasoning behind how edges are defined. It's important for us to not only show how graphs are built but also to elaborate on why our chosen method is beneficial for the prediction task. We recommend that benchmarks always include well-tuned baseline comparisons to highlight the advantages of the structural information we use. Specifically, benchmarks should report the performance of baselines that only analyze unstructured node features or graphs based solely on similarity. We believe that a poor benchmarking culture is a significant barrier in the graph learning community, leading to inconsistent evaluations and inflated performance reports, especially with small datasets like MUTAG. New architectures are often compared unfairly to outdated baselines, and the community tends to overlook the significance of small improvements. For example, while zinc tasks can be solved with standard tools, minor enhancements are often overemphasized. Additionally, a lack of knowledge in molecular and material modeling limits our understanding of tasks, as many state-of-the-art models ignore important relationships between 3D structures and molecular properties. To tackle these issues, we need to create practical tasks and robust evaluation frameworks. Unlike other fields, graph learning lacks reliable benchmarks that are resistant to manipulation. We propose establishing expert-validated benchmarks and competitions, similar to Kaggle, to assess models across various domains. We should focus on larger, relevant datasets to improve data quality and encourage collaboration across disciplines to translate real-world problems into graph learning tasks. For 2D molecule generation, we should prioritize benchmarks like MOSIS and GUACAMOL over outdated ones. Future efforts must enhance computational efficiency and incorporate larger datasets with diverse properties. Evaluations should include error bars and combined metrics to provide a clearer picture of performance. Finally, we note that there is currently no true foundation model for graph learning, unlike in deep learning where large pre-trained models exist. While some domain-specific graph models have emerged, their performance often shows only slight improvements over standard models. We face challenges such as varying requirements across tasks, the need for new strategies in graph representation, and the limited availability of graph data compared to text. Addressing these challenges is crucial for advancing graph learning. Section Summary. In this section, we highlight the need for improved benchmarking practices in graph learning, emphasizing that not all phenomena should be modeled as graphs and that benchmarks must systematically evaluate the advantages of relational frameworks. We advocate for the development of robust, expert-validated benchmarks and larger, domain-relevant datasets to enhance model evaluation and address the current inadequacies in the graph learning community. Section: Suggested Remedies. In this section, we address the suggested remedies for the challenges faced in graph learning. We recognize that graph-focused models and robust benchmarking are essential for the advancement of graph learning alongside other deep learning fields. We propose a shift from using a separate model for each dataset to employing a single model that can handle all datasets, allowing us to better assess model performance across various graphs. For instance, instead of training different models for each task in a 5-task benchmark, we advocate for training one model that can manage all tasks. In more complex scenarios, like combining classification and regression, we recommend an encoder-processor-decoder framework. This involves pre-training a unified backbone model and then fine-tuning specific encoders and decoders for each task. We also emphasize the importance of creating large-scale, high-quality datasets that include a variety of graph structures, such as sparse, dense, homophilic, heterophilic, directed, and multi-relational graphs. We suggest filling data gaps with synthetic data and ensuring that known test sets are excluded from pre-training datasets to maintain data integrity. We note that fields related to graph learning, like geometric deep learning, are thriving and achieving significant successes. Geometric deep learning has led to advancements in areas such as structural biology and material science, and it supports state-of-the-art interatomic potentials for accurate atomistic simulations. This field focuses on 3D objects and addresses the inherent symmetries and invariances in the data. Its success is linked to real-world applications, including notable advancements in protein design and the development of foundational models for practical tasks. While graph structure can be beneficial in geometric deep learning, it is often secondary, with inputs treated as fully connected graphs or point clouds. In contrast, traditional graph learning on molecules deals with 2D objects where graph structure and permutation symmetry are crucial, but often lacks the rich 3D information that is vital in geometric deep learning. To support our previous claims, we provide empirical evidence. We previously raised concerns about the lack of meaningful correlation between graph structures in common benchmarks and the intended learning targets. We present further evidence by referencing a recent message passing scheme that, during odd layers, ignores the original graph in favor of a fixed structure expander graph, specifically a Cayley graph. Ablation studies on various benchmarks showed that using only the Cayley graph sometimes improved performance, even though it does not encode task-relevant information. This aligns with findings that regularizing graphs consistently enhances performance. We replicate these experiments using OGB graph-level benchmarks to strengthen our claims. We also evaluate a baseline where we remove the graph structure entirely, allowing the model to operate on an empty graph. Due to space constraints, we provide detailed experimental information in the appendix, including dataset specifics and tuned hyperparameters. Our results indicate that in 5 out of 9 experiments, the regular Cayley graph either outperformed or matched the original graph's performance. Notably, for the MOLB-BBP datasets, the highest performance was achieved when the graph structure was completely omitted. We also reassess the evaluation practices for GNN architectures, particularly regarding the use of outdated reference results to measure performance improvements. This often leads to overestimating the gains of newer architectures. We illustrate this issue using the PCQM4MV2 dataset, which is popular for demonstrating the performance of graph transformers over simpler models. Previous evaluations cited results from the 2021 OGB-LSC competition, suggesting a validation mean absolute error of around 0.12 for standard models, while graph transformers achieved below 0.09. We aim to re-evaluate this performance difference by retuning the hyperparameters for the GINE model. We conduct our experiments using the same giant architecture and make minor adjustments to align with current practices. Our findings show that even without additional features, tuning the model configuration reduces the error by over 20%. With added structural features, performance improves further, making it competitive with several graph transformer baselines. Our results highlight the fragility of empirical evaluations in GNNs and suggest that reported numbers often do not accurately reflect the true progress in model capabilities. Section Summary. In this section, we emphasize the importance of developing unified models for diverse graph datasets and advocate for high-quality, large-scale datasets to enhance graph learning. We also highlight the need for rigorous empirical evaluations, demonstrating that outdated baselines can misrepresent the performance of newer architectures, as shown in our reassessment of GNN results on the PCQM4MV2 dataset. Section: The meaningfulness of architectural changes. In this section, we discuss the importance of architectural changes in our evaluations. We highlight the fragility of graph neural network (GNN) assessments in node prediction tasks. A set of heterophilous graph datasets was introduced to test various GNNs, including both standard and heterophily-specific models. The authors of these datasets used official implementations for the heterophily-specific GNNs but modified the baseline GNNs by adding a two-layer multi-layer perceptron after each neighborhood aggregation layer. While they noted that this change improved performance, they did not investigate its effects in depth. This raises important questions about the fairness of their comparisons. 1. They did not set a parameter budget, which could lead to models with different capabilities. 2. The baseline GNNs were evaluated using a consistent protocol, while the heterophily-specific GNNs were assessed with their own codebases, which might have different architectural choices, creating potential bias. 3. The specific baseline GNN setup, including the added two-layer MLP, a linear encoder, a linear decoder, and JELU activation, was acknowledged but not thoroughly analyzed, leaving its role in performance improvement unclear. These issues make the performance comparisons less meaningful. Although the proposed datasets could be useful benchmarks for heterophilous graphs, their effectiveness cannot be fully determined without a proper evaluation protocol. This emphasizes the need for such protocols, as even the best benchmarks require clear evaluation guidelines to assess their quality reliably. To validate our concerns, we re-evaluated the baseline GNNs, including GCN, SAGE, and GAT, using a new codebase that followed the reported hyperparameters but excluded specific architectural changes. We removed the linear encoder, the two-layer MLP after each aggregation layer, and the linear decoder, and replaced JELU activations with standard ReLU. Our results showed significant average performance gains of 43.56%, 14.63%, and 19.49% on the Roman Empire, Amazon ratings, and Minesweeper datasets, respectively. This analysis does not question the validity of the proposed benchmarks but highlights the critical need for evaluation protocols that include fixed model size limits and clear guidelines on architectural modifications. Next, we explore multi-task pre-training and fine-tuning using an encoder-processor-decoder framework. We aim to investigate this approach across various domains, including vision, function call graphs, large molecules, and social networks. Our goal is to gather initial insights on the effectiveness of this architectural pattern when pre-trained on a mix of different graph tasks, even on a smaller scale. We believe that positive outcomes from our experiments could encourage the community to develop a large-scale, curated pre-training corpus, along with standardized setups and evaluation procedures. We train domain-specific encoders, such as those embedding atom and bond types in molecules, and task-specific decoder MLPs. For the processor network, we evaluate both a message-passing neural network based on the GINE architecture and a graph transformer with soft attention bias and RWSE structural encodings. We create two sets of datasets, one for pre-training and another for fine-tuning. During fine-tuning, we freeze the processor weights and learn a new encoder and decoder. If possible, we reuse the encoder from one of the upstream datasets. Additionally, we train baseline models with the same architectures as our pre-trained models but from scratch in a single task manner. Our upstream mix includes datasets like PCQM4MV2, COCO-SP, and MALNETTINY, which vary in application domain, prediction task type, and graph size and sparsity. We do not expect strong transfer between these tasks during pre-training. Instead, we aim to see if our MPNN and graph transformer models can learn general graph representations useful for multiple, potentially unrelated tasks. To support this, we also train an empty graph baseline in the multi-task setup, where the processor network is set to identity, ignoring the graph structure. Our results show that both the MPNN and graph transformer perform significantly better than the empty graph baseline and their randomly initialized counterparts across all three tasks. While they do not surpass their single-task baselines on COCO-SP and PCQM4MV2, surprisingly, on MALNETTINY, both models outperform their single-task performance when trained in a multi-task setting. Section Summary. In this section, we highlight the importance of standardized evaluation protocols for GNNs, as our re-evaluation of baseline models without architectural modifications revealed significant performance gains, emphasizing the need for fair comparisons. Additionally, we explore multitask pre-training using an encoder-processor-decoder framework across diverse datasets, aiming to assess the generalizability of graph representations and the effectiveness of our models in various tasks. Section: Downstream Mix. In this section, we evaluate how well our pre-trained multitask models adapt to new tasks. We create a downstream mix that includes three datasets with varying similarities to our initial data. Specifically, we choose Pascal-Voc-SP, peptides, struct, and stargazers. We measure performance across different fine-tuning steps to see if our pre-trained models are more efficient with fewer samples compared to single-task models. Our findings indicate that pre-training is generally helpful, especially with fewer optimization steps, though the benefits vary based on the target dataset and model type. We see strong performance on Pascal-Voc-SP and good cross-domain results on stargazers for both model types. However, the results for peptide struct are less clear. The pre-trained GT shows some transfer, but the pre-trained MPNN performs poorly at certain steps. Overall, our results suggest that both MPNNs and GTs can learn useful graph representations that transfer well to different tasks.